Now let's talk about complex numbers in physics and engineering as we continue to deal with the applications of complex numbers. In the last video, we saw complex numbers as they are deployed in differential equations. So let's see what we have here. So, first of all, again, why complex numbers matter in physics and engineering, right? Complex numbers are essential tools in physics and engineering because they simplify problems involving oscillations and waves, electrical circuits, signal processing, quantum mechanics. So, a complex number is written as z equals a plus bi. We know that already, where a is the real part and b is the imaginary part, and I actually means square root of negative of 1, square root of minus 1, that is. So the geometric interpretation is this, that a complex number can be represented in the complex plane. So the horizontal axis represents the real part and vertical axis represents the imaginary part. I demonstrated all that when we started out this playlist. Then in the polar form now, you have z to be r into cos theta plus I sine theta. In exponential form now, since cos theta plus I sine theta, according to the Euler formula, is the same thing as is the same thing as e raised by I theta, then z will now be r e raised by I theta, where r now is the modulus of z, which is the same thing as square root of x squared plus y squared, for z equals x plus iy, that is. And theta is the argument of z. Okay, theta is the same thing as arctan of y over x. So, of course, I just talked about the Euler's formula, and it's a key identity in complex numbers that e raised by I theta equals cos theta plus I sine theta. This allows us to replace trigonometric expressions with exponentials, which are easier to manipulate. So sometimes it's easier to deal with exponential expressions instead of trigonometric expressions. So we get to switch back and forth between exponential and trigonometric expressions depending on the kind of task we have at hand. So operations with complex numbers, of course, I talked about all of this in the very early videos. So you can, to add complex numbers, if you have a plus bi plus c plus di, you add real to real, that's a plus c, and complex to imaginary to imaginary, that's b plus d I. So this I with them is what makes them imaginary. And for multiplication, we have a times c, ac, a times di, we have adi, bi times c, we have bci, then bi times di, that's bdi squared. That I squared is minus 1. That's why we have minus bd here. It's minus 1 rather. So that's why we have minus 1 bd. That's minus bd, which we have here. So for multiplication, we have this. And for conjugates, we say z star is a minus bi. So the conjugate of z, which is a plus bi, is actually z star, which is a minus bi. And then the magnitude of either the conjugate or the complex number and its conjugate, the magnitude is the same. So that's the modulo z, which is square root of a squared plus b squared, or x squared plus y squared, if you like. So 31. So the next thing is we talk about the one application in engineering and physics. We talk about oscillations and waves. So a cosine wave, given as x of t equals a cos omega t, using complex representation, x of t is equal to the real part of a e raised by I omega t. So if you differentiate, it becomes differentiation. Now you have this complex wave, right, which you can rewrite in the complex form this way. And then if you differentiate, it now becomes d dt of e raised by I omega t. And if you differentiate I omega t, you get I omega multiplied by e raised by I omega t. So it's easier to deal with this when it is in polar form than when it is in the other form. So, and by putting this rule, it means that after you are done with everything, you just need the real component of the result. So a very good example of this is this. Imagine you have a wave, x of t equals 5 cos 2 theta, and you convert to x of t equals re. Cos 2 theta is from Euler's formula, right? E raised by I theta is cos theta plus I sine theta. So because this is just cos now, they say if you want to write this in terms of polar form, this will be real part of 5 e raised by I to t, because this e raised by I to t is actually going to be cos 2t plus I sine 2t, but you need just the real part. Okay, so if you differentiate this now, d dt, if you differentiate this, you get 5 times I2, that's 10i e raised by I to t. So the final result then for dx dt would then be minus 10 sine 2t, like that. Okay, so because this I outside now is going to affect the cos, it will make the cos imaginary, it will make the sine uh, real, and that's why the final result here is minus 10 sine 2t. So you differentiate that, and of course we can actually plot it. We can have cosine via complex exponential, and we have the real cosine, and you see that they match perfectly, right? So if you talk about the real part of 5 exponential 2t, so with the real cosine, everything is just perfectly aligned like that. So they are basically the same thing. So then we go to another application, which is in the area of AC circuits. So for AC, that AC is alternating current, right? So V voltage is given as V of t equals V naught cos omega t. In complex representation, you have V equals V naught e raised power I omega t. And the impedance can be for impedance, you have the resistor R, inductor I omega L, and capacitor 1 over I omega c. So from Ohm's law, now we then have V equals IZ. An example, you have the resistor of 10 ohms, the inductor of 0.1 Henry, I think. Then you have omega, the angular, so 50. So the impedance can then be given as Z equals R dot I omega L, which is R is 10 plus I omega, that's 0.1 times 50, which is 5I. So the magnitude then is square root of 10 squared plus 5 squared, and you get square root of 125, which is approximately 11.18. So you can do that using your Python code, So you have R to be this, L is that, omega is this, and then you define the formula. So Z is R, the complex parts, I omega L, and then you get impedance to be 10 plus 5j, you get the magnitude to be 11.18, blah blah, and then you get the phase in radians to be 0.46 and all that. So, and the way to extract that, you see, you get the angle of Z here, that's 0.4636 and all of that. Then we have application of complex numbers in signal processing also. Using complex exponentials, we know that e raised by I omega, we have e raised by I omega t, and the Fourier transform x of omega is integral of x of t e raised by I omega t dt. An example, if you have x of t to be cos 3t, the equivalent form would be x of t equals half e raised by I 3t plus e raised by minus I 3t. So you have that going easily like that. And then you can also plot that on a frequency spectrum like this. So you have this, and then we have application in the area of quantum mechanics. So if you have wave functions, psi of x comma t equals e raised by I into kx minus omega t. Probability density can be given as absolute value of psi squared is psi star psi. So in this case, complex numbers encode phase and interference effects in quantum mechanics. And then we have another application in rotations. So, at some point we talked about transformations of complex numbers, where we talked about things like rotation, scaling, we talked about translation, and I think there's also, yeah, I think there's another one, rotation, scaling, translation. Um, yeah, there's one more that I'm not remembering right now. So if you multiply by e raised by I theta, that rotates a complex number, so z prime then becomes z e raised by I theta. So it rotates it. A good example of that is when you have z equals 1 plus I. So by 90 degrees now, you have z prime to be 1 plus I e raised by I pi theta. So that's like multiplying by cos 90 plus I sine 90. And then z prime becomes, this whole thing is I. This whole expression is I, because sine theta is 0. So cos theta, cos 90 is, so sine 90 is 0, but cos 90 is 0, but sine 90 is 1. So that's why you have this I left here, so that you now have 1 times I times I, that's minus 1. So z prime now is 1 minus I. So you have that rotation by 90 degrees. So the rotated value now becomes something like this. So, I mean, I've done videos on the transformations, so you can visit, refer to those videos, and you see what translation, rotation, scaling, and all of these things look like. Okay, so we talk about some in the summary now. We are saying that complex numbers simplify oscillations and waves. Then they convert differential equations into algebra, and they represent magnitude and phase simultaneously. So they are more like they help to encode oscillations and waves very precisely. And then they are fundamental in electrical engineering, signal processing, quantum mechanics, and control systems. So for practice problems, we have questions 1 to 10, and then we have questions 11 to 20. As usual, I'm going to solve two of them, and then we'll go on to the next video. So I'll be solving problem 1 and 13 in this case. Problems 1 and 13. Problem 1 says convert 5 plus 12i to polar form. Find r and theta. Then problem 13 says to find the impedance of a circuit with r equals 5, l is 0.5, and omega is 10. So let's go for that and see how it all pans out. So problem 1. So we have problem 1. So we want to convert 5 plus 12i polar form to polar form. Of course, to do this, first thing, we compute the magnitude. We compute the magnitude. So we can say that Z equals 5 plus 12i. So in that case, the magnitude, okay, the magnitude now is modulus of z, which is modulus of 5 plus 12i. And that simply means square root of 5 squared plus 12 squared. So that is equal to square root of 25 plus 144. So 25 plus 144 is equal to 169. So square root of 169 is simply 13. So what we call R, which is the magnitude of Z, is actually 13. So in polar form, it is R, right? So that's 13. So the next thing we want to do is to compute the argument. Of course, we already know that polar form. So we know already that polar form is of Z is R e raised by I theta. So it means we need R and we need theta, and then we'll be fine. So that's the idea of polar form in general. So we need R and theta, and then we have polar form. So R is already computed. So the next thing we need is to find theta. So now we compute the argument. Now we compute the argument. The argument is the angle theta. So now we compute the argument. So, and that is simply giving us theta, which is equal to the inverse tan of y over x, you know. So y over x in the sense that z is x plus iy, and that is 5 plus 12y in this case. So that implies that x is equal to 5, x is equal to 5, and y is equal to 12. So if that is the case, we are saying that theta is equal to arctan of y, which is 12, and x, which is 5. So if we do this, we have theta um, to be approximately 1.176 in radians. Okay, so in case you're wondering how to get this right, you can just use your Google. So just come to Google and do arctan. So just do arctan, arctan 12 over 5, 12 over 5, then in radians. So it's already giving that to you in radians like that. So this is in degrees. Now, if you want it in radians, just say radians here. Radians. So we want it in radians. Say radians, radians, radians. In radians. Yeah, that's 1.1760. And that's exactly what we have there. 1.176, so you can do that. So now that we have r and theta, then everything is ready. So we then say, the final polar form, as we know it, it is z equals r e raised to power I theta. So, and that means we have z to be 13 e raised to power I. Theta is 1.176. So z is 13 e raised to power 1.176. Maybe I 1.176, like that. So that actually takes care of that problem. Of course, this uh yeah, I think we can leave it that way. Let's go on to the next problem, to the next one. That's problem 13. Problem 13. So for problem 13 now, we need we need find to find the impedance of a circuit with R equals 5, L equals 0.2, and omega equals 10. So that's what we need there. So we know that formula for impedance is Z equals R plus I omega L. So that means that Z is 5 plus I into 10 times L, which is 0.2. So 1 times 10 times 0.2. So Z now is equal to 5 plus 2i. 10 times 0.2 is 2. So 5 plus 2i, that is what the impedance is. So then what we need the impedance, right? So formula for impedance, we got that already. So, but we need to, so we got it in terms of complex number, but we need to also get it we need to express it, the magnitude and all that, and the angle. So we know that the magnitude will simply be absolute value of z, which is square root of 5 squared plus 2 squared, and that is square root of 25 plus 4. So that means that the magnitude, absolute value of z is root 29. So we have that right there. And then for the face, which is theta, right? That's theta equals of arctan of 2 over 5. Y here is 2. X is 5. Y is 2. So we need arctan of y over x. That's arctan of 2 over 5, like that. So that means theta is approximately 0.381 in radians. So final answer now. Final answer, we can give the suite. Z is 5 plus 2i. Then absolute value of z is root 29. And then theta is approximately 0.381 in radians. If you want it in degrees, that's also possible. So with that, we come to the end of this video about applications of complex numbers in physics and engineering. Don't forget to try your hands on the questions. Here you have 1 to 10 and then 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel also by clicking on join. That gives you special privileges like getting to see some videos first or seeing some videos exclusively All right. Beyond that, you can request for PDF copies of my notes. You can also hang out with me physically or online to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.